chapter 6, our first section of chapter 6. You guys ready? Tell me, what do we call it when I have an equation that has a dy dx in it?
Differential equation.
Thank you very much, Daniel. Yes, it is called a differential equation, the first bold-faced thing. Tell me, if I give you a differential equation and I also give you a point on the solution curve, what do we call it? What kind of problem is it called now?
Initial value.
Yeah, initial value problem. And that point I give you is the initial value. There's another name for that point I give you on the solution curve besides the initial value. What else do they call it? Yeah, it's called the initial condition. Good. And then finally, or not finally, but if we find all the functions y that satisfy the differential equation, then what have we done?
Solved.
Right, but what the problem is in solving the differential equation, you've just found a family of curves or a family of solutions. To find the particular solution, you're going to have to use your initial condition to find the, well, I guess I already said it, the particular, did I say that word? But, oh well. But it's the particular solution that fulfills the initial condition, and so we've solved the initial value problem. Hey, let's go ahead and do an example, okay? Here comes like this incredibly simple example. I've got dy dx equals the sine of x, correct? Well, if I want to solve for y, what do you suppose I'm going to have to do to both sides of the equation? Yeah, take the antiderivative. So I'll take the antiderivative of both sides of the equation. The left side becomes y, and the right side, and in fact, what I really should do is at this point, I should multiply both sides by dx. So I get the integral of dy equals the integral of sine of x dx. That's proper form, okay? So I've taken the antiderivative of both sides of the equation. Then to do it, the antiderivative of dy is y. The antiderivative of the sine of x is the negative cosine of x. But the problem is, the negative cosine of x isn't the only function where if I take the derivative of it, I get the positive sine of x, right? It could be the negative cosine of x plus 1 or the negative cosine of x plus 7. And so because there's an infinity of solutions to this, there's an infinity of functions whose derivative is the sine of x, I put this guy c there to show the world, hey, you know, there's actually an infinite number of solutions, negative cosine of x plus any constant I want. By the way, do you remember what we call this, the constant of, did I ever teach that to you? What's that? Okay, it's called the constant of integration. And I may have, I thought I introduced it when I taught you Leibniz thingy, but maybe not. So I'm going to say it now. It's the constant of integration. And boy, you're going to see that a lot. I'm going to talk about the constant of integration all the time. Because finding the particular solution actually just means finding the constant of integration. That's what you're doing. Finding this particular solution is just finding the constant of integration. And the way I'm going to find the constant of integration is by using my initial condition. in this case, my initial condition is, what do they say, y of 0 equals 2? When x equals 0, y equals 2, that's my initial condition. So I'm going to stick it in. I'm going to have a 2 for y, negative cosine of 0 plus c. The cosine of 0 is 1, so I end up with 3 equaling c. So I get y equals negative cosine of x plus 3. And this here is the particular solution. You guys ready to do one on your own? Yeah. All righty. Okay. Let's say I told you that dy dx equals e to the x, and the solution contains the point 1, 0. Find the particular solution. And I want to tell you again, you take the antiderivative to solve the differential equation, but then you have to use the initial condition to find the constant of integration to get the particular solution. So good luck. Do it in my head. Okay. What you got? Do it. Oh my God. Oh my God, Angel. Good work. Oh, you lazy bums. Yeah, you're on the way. Now you're gonna find your constant of integration and then you get your answer. See how easy this is? This is like yeah. CD, wait, what's that on there for? The other one of the new yes is do the x. Oh my God. Yeah. No, just the x plus c. Just e the x plus c. Don't overthink it, Zach. Don't overthink it. Just pretend you have 20 fewer IQ points and see, you're smart. Good for you, buddy. Yeah, Steve. Cool. Coolio. Oh my gosh. Yeah, sure. You earned it. You earned your trip to that. Good for you. Keep going, young lady. Yeah. Don't doubt yourself. Keep going. Yeah, you're right. That's all there is to it, man. Okay. The thing is, x is 1. See how it contains 1, 0? Your x is 1 and your y is 0. So you got it flipped. I faked you out. I successfully faked out. Good for you, Fatima. Let's see what you got. Okay, but e to the first is e to the first, so you subtract e to the first from both sides, you got c equal negative e to the first. Okay, good for you. I mean, you can just keep it even first, and then call it 2.71 or whatever. Dude, I crushed you. Good for you. I crushed you. Okay. No, you're a left-hander. Here, let's see the correct answer. Oh,
I didn't jump off before this. Grabbed you. Yeah, he grabbed me, like put me in a headlock, and was like, tap.
So you guys are getting this, right? That step one is to take the antiderivative of both sides of the equation. Again, proper form would be to multiply both sides by dx, so your integral looks like your normal Leibniz form, alrighty? And then you get y equals e to the x, because the antiderivative of e to the x is e to the x plus c, and I stick in a 0, you know, this is x and that's y, so I stick in a 0 for y and a 1 for x, and I get c equaling negative e to the first, or just negative e if you prefer. And so my y ends up being e to the x minus e. Yeah, there it is. There's my particular solution. Hey, not very hard. Let me see if I can find a harder problem for you.
Okay, let's remember you don't give us the initial condition and make us find the actual equation.
What's that?
Where you don't give us the initial condition.
Well, if I don't give you the initial condition, then yeah, you're just taking the antiderivative of the thing. Here, just a second. Wow, this is going really fast. I could teach so much more. Yeah, ooh, here's one. Yeah, you're not going to get this one. Sorry, kids, I feel so bad for you, but don't feel dumb just because you don't get this.
I'm going to
Okay. Okay. Please get me the particular solution. Good luck, guys. Good luck. This is problem 34 of tonight's homework, which you aren't doing, so I can feel free to give it to you. Yeah, that's a cough syrup. Either it's placebo effect or early works. One of the two. Shoot, I wish I could make it darker. Are you guys remembering that the antiderivative of 1, what's the antiderivative of 1 over x? Okay, good. If you remember that, then you're fine. In fact, I think I'm going to show you one more thing. Yeah, I'll show you one more thing. You guys done? Okay, cool. Then let's go for it. Okay, first of all, dy equals 1 over x dx, and then you take the antiderivative of both sides. So you get y equals the log natural. And I got to tell you, it's not the log natural of x, it's the log natural of the absolute value of x. And I need to teach you why that's so. And so that's the last thing I'm going to do with you guys today, plus c. But remember, the antiderivative of 1 over whatever is the natural log of the absolute value of that thing. You know, when it's just 1 over x, I mean. Okay, great. So now when y is 0, when x is e to the third, so I got negative 3 equals c, so y equals the log natural of the absolute value of x. Oops. Minus 3. How many people got that problem right? Okay, hey, good for you guys. Alrighty, then, you know, on tonight's homework, they're also going to start you with the second derivative of this stuff. That'll be kind of fun, you know. Hey, let me just, I'm not going to go through all the awful details, but I'm pretty confident that you guys will be able to figure it out. What if I gave you this? What if I told you that the second derivative equals, let's say, 5, let's make it even. Let's say it's equal to 6x, and y prime of 1 equals 2, and y of 0 equals 4. Let's say I told you that, okay? You tell me, I've given you an expression for the second derivative. What do you suppose your process is going to be? Yeah, take the antiderivative twice. In fact, you'll take the antiderivative once, you'll sprout a c.
Yeah, find that c.
Yeah, find that c, and then take the antiderivative again. You sprout another c and find that new c. You guys okay?
Yeah.
So something like this, I would take the antiderivative of both sides, which I'm not going to go, well, I guess I'll show you. This d squared y over dx squared. Okay. What this is really a dumb way of actually expressing this. Okay. The derivative with respect to x of dy dx, that's what the second derivative is. And so what we do is we multiply both sides by dx. So I have d dy dx equals 6 dx. And now I can take the antiderivative of both sides of the equation. So d whatever, the antiderivative of the d goes away, and I just get dy dx equals 6x plus c. And then y prime of 1 is equal to 2. So when x is 1, this guy is 2. So I get negative 4 equals c. So I get dy dx equals 6x minus 4. And then I do it again. And thank you, Fatima, for doing this thing. So I get dy equaling 6x minus 4 dx, and then I take the antiderivative of both sides, so I get y equals, wait, what? Where'd my x go?
Leave it.
Hi, Dad. So it's 3x squared, right?
Yeah.
Oh, I just totally messed this problem up. What a good teacher I am. Okay, so that's negative 1, right? My bad. Negative 1. And this is still 3x squared. Okay. Okay, is that good now?
Yeah.
Does that look good to you guys? I took the antiderivative of 6x and got 6x, which is not right. Yeah, okay. All righty. So now I'm going to take the antiderivative of 3x squared minus 1 dx, which gets me x to the third minus 3, wait, x to the third minus x plus c. And now I'm going to stick in that new initial condition. Y is 4 when x is 0. So I get c equaling 4. So I get y equaling x to the third minus x plus 4. So what Leilani said was correct. You're going to do it twice. You'll do it once and use the initial condition involving the first derivative to find that first constant of integration, and use the initial condition involving the function itself to find the second constant of integration. And I think it'll go fine. I think you guys will be great. Okay. Why is the integral of 1 over x dx equal to the log natural of the absolute value of x plus c? Why do I have to have that absolute value there? Why is the antiderivative of 1 over x equal to the log natural of the absolute value of x? I'll tell you why. Because the derivative of the log natural of the absolute value of x equals 1 over x. That's why. That's the same answer I could give to any antiderivative. Why is the antiderivative of 6x equal to 3x squared plus c? Because the derivative of 3x squared plus c equals 6x. Well, this is no different. But now I need to actually demonstrate to you why the derivative of the log natural of the absolute value of x ends up getting me 1 over x. So here it comes. The log natural of the absolute value of x is actually a piecewise defined function. Now x can't be, x can't be 0, alrighty? Because you can't take the log natural of 0. But you can take the log natural of a positive number. So when x is greater than 0, this absolute value is of no account, and I have the log natural of x. Okay? But when x is less than 0, when x is a negative, then the absolute value takes the opposite of x. That is, if I put a -2 in there, then I'm taking the log natural of +2. Or if I put a -5 in there, then I'm taking the log natural of +5. So I want you to see that when x is less than 0, this function is actually the log natural of negative x. You guys okay with that? Okay, so now let's go ahead and take the derivative. The derivative of the log natural of the absolute value of x is going to equal the derivative of each of these guys individually. Well, the derivative of the log natural of x is 1 over x. We learned that. The derivative of the log natural of x is 1 over x. The derivative of the log natural of negative x is going to be 1 over negative x multiplied by the derivative of negative x, which gets me 1 over x. So whether my x is negative or positive, the derivative gets me 1 over x. And so since the derivative of the log natural of the absolute value of x is 1 over x, that means the antiderivative of 1 over x is the log natural of the absolute value of x. Does that make sense? Hoping so. Yeah. That when you take the derivative of the log natural of x, you get 1 over x. Whether x is positive or negative, you get 1 over x. So I don't know how many more times I can say it, so I'll just be quiet. Any other questions or issues? Okay, well, then I'm done.